Going on to Chapter 7. In Chapter 7, we skip 7.1 and start with 7.2. Now your quiz me's and your study plan will all reflect this, so you don't have to worry about 7.1. And all those items were taken out of the test. In 7.2, we're talking about sets. And this is a topic we mentioned in a number of other subjects that I've taught. What is a set? Well, a set is a collection of items. And it could be a set of dishes, a set of tableware, a set of stamps. But in mathematics, it's a set of numbers usually. And what we're going to look at are properties of these sets and then set notation. Well, first off, we say that a set is usually defined by, let's say, a letter A or a capital letter B, capital letter C. This is how we would define the set. And then the items in the set would be called elements of the set or members of the set. Now we're going to look at a couple of little symbols that come along. This funny looking E here, the definition of that is A is an element or a member of set A. That'd be lowercase a. And another use of that symbol would be lowercase b with a slash through the symbol is not an element of set A. So we're just describing the name and how these symbols function. Now every once in a while you might run into a set without elements. If it doesn't have any elements in it, then we say the set is an empty set. Another synonym for empty is a null set. And the symbol for that is a 0 with a line through it. That's the one that's in our textbook. I've seen this in other textbooks where they have brackets, but there's nothing between the brackets. So that would indicate an empty set. And then going on to set builder notation. Set builder notation is a bracket, which I don't make them too well. And we would say X is such that X is a real number. So you're defining what's in the set and then the rule that the set works on. And we end it with a brace. I guess these are called braces. While a bracket is this. We use those in other things. Again, all of this is in your book starting on page 343, and we'll be doing examples and giving you some information as we go along. Continuing with the set notation, in example 1 we're representing sets, and there's the rule method or the listing method. Now for the rule method, we use that set builder notation. X is such that X is a weekend day. Now the weekend days we know are Saturday and Sunday. So we have listed the elements of the set. This is the rule that we're following. In mathematics, we'll say that X is such that X squared equals 4. Now, if you were to solve that, and the method of solving it, you might recall, take the square root of this, plus or minus the square root of that, we get x equals plus or minus 2, which is what we have in our listing method. Just a little bit of algebra. Now, this next one's a little bit redundant. It says x is such that x is a positive counting number. Well, counting numbers by definition are positive. So this is where I think it's a little redundant, but that's the way it says it in our book. And that would be the counting numbers start at 1, then 2, then 3, and then we put 3 little dots to indicate that same pattern continues. This is called an ellipsis. These 3 dots are called an ellipsis. That means the pattern continues. I added that one actually. This is the one that's in the book. X is such that x is an odd, they put the word positive, counting number. So odd counting numbers would be 1, 3, 5, and then our ellipsis to indicate it continues. So the thing to remember, this is the rule method, this is the listing method. Another couple of key words. A set is finite if there is a particular given number of items. So here we say this set contains 1, 2, 3 items, and that's the full set, so that's a finite set. We say a set is infinite as we look at a set and it starts at a pattern but goes on and never ends. This implies it's going on to infinity. So that's why we call it an infinite set. Now, a combination of this a little bit would be if you start off, there's your initial pattern. You're leaving some elements out, but you're saying it ends at 21. So if we wanted to define this, the rule of this would be x is such that x is a positive, odd counting number less than, now 21 is in the set, so it would be less than 22. That would indicate 22 is not in the set, or, yeah, we could say it that way. Okay. This example wasn't in the text, but I think it's possibly of interest. Continuing, this is a new symbol. It looks like a letter C, but it's a sideward U, and it reads A is a subset. So this item right here indicates a subset. Put that in red here. This is the term for a subset. So it's saying A is a subset of B. A equals B states that set A and set B have exactly the same elements. And one of the things I didn't mention before is that when you list elements, like the first 3 counting numbers, which would be 1, 2, 3, normally we would write it that way. But if you wrote it 3 or 2, 1, 3, these are equal. It doesn't have to be in a particular order, But I think, and you know, if you're going to read it, it's easier to put it in order. But according to our text, it doesn't have to be in order. And if an element is repeated, so if you had the numbers 1, 1, 2, 3, 3, again, the 1s are repeated, the 3s are repeated, you would list the elements of that set this way. You don't repeat them. Okay, again, a slash through this symbol, sideward U, is that it's not a subset of B. And again, a slash through an equal sign, it says set A and set B do not contain the same elements. Now, this from a previous page, it says an empty set. And it's logic that we skipped in section 1, but just take this as a given. An empty set is a subset of every set. A null or empty set is a subset of every set. And here's kind of makes sense too. If A is a subset of B and B is a subset of A, then A equals B. Again, this is tying into the logic that we skipped in 7.1, but again, just take these as givens now. Going on to example 2 on page 344, we have defined by listing 3 sets, set A, set B, and set C. Notice A is sort of in order. And I should check that here. Comma, there we go. Set B contains the same elements as set A, but in a different order. And set C is in order. It has some of the elements, but not all of them in set A and B. So we're looking at these statements down here. Set A equals set B. Well, we said they contain the same elements, so that's true. Now, this one says that set A is a subset of C. That is, some of the elements in C are found in A, all of them, by the way. And that is true. A is a subset of B. Well, that's true, because all the elements in B are found in A. That's why they are equal. Set C does not equal set A. There are more elements in set C than in A. They don't equal. Set C is not a subset of set A. That's true, because in set A there are not all of these elements. B is a subset of A. We said that. In fact, these two go together, and these two equal this that we said earlier. Now, we also said that every null set is a subset of every set. So, an empty set is a subset of A. That's true. An empty set is a subset of C. That's true. Now, if we didn't have this line through it, but what this is saying, that an empty set is not a member of set A. It is, but it's not a subset of set A because it's an empty set. Continuing on with example 3 on page 344, it says list all the subsets of the set A, B, C. Really feel like a teacher now with my ruler. So a subset of this would be all of the members. Another subset would be the first two members, the first and the third, the second and the third, and then subsets of all of these are the letters themselves. And remember, 0 is a subset, an empty set, not 0. An empty set is a subset of every set. Now as we move on, they're asking us to discuss this and say, which of them are true? Is a null set a subset of a null set? Well, since a null set is an empty set is a subset. I think this is true. Again, they don't tell me the answers, but I will double check them for you. Now, this symbol is an element or member. Now, this is an empty set. Is an empty set a member of a empty set? I think this is false, because this doesn't have any members or sets. Well, it has a subset. This one we said was true, but I believe this is false. That's why we're discussing it a little bit. Now, how about if you saw something like this? An empty set is the same as a set that includes 0. No, this is not true, because this set has a 0. This one doesn't, so they're not the same. This one I know for sure is false. And is 0, or let me put it this way, is an empty set a subset of this? And the answer is yes. We said that a null set or an empty set is a subset of every set. As we move on, we're going to look at some other symbols in set operations. Now, the symbol for a union of sets is this U. It combines elements of whatever you're putting into union into one set. So a way to look at the rule, A in union with B would be such that X is a element of A, or X is an element of B. And another useful tool is the Venn diagram, where we have a square representing our whole field, and then specifically within that we have a circle that is set A, a circle that is set B, and notice they're overlapping a little bit, but by coloring in everything, this indicates in a Venn diagram format the union of those two sets. It's sort of nice to see a diagrammatic representation, an illustration of what's going on. And as we read it here, we're saying that A is a subset of the union of A and B, and so is B a subset of a union with A and B. Remember, this is that special letter that in your mat palette of tools, they give you that as one of the tools if you ever need it. Now, in this next part, where I have illustrated a union of these two sets, another term that is mentioned is intersection. And the symbol for an intersection is an upside down U. So again, I didn't make it too great. And what this means is we are only interested in finding those elements in set A and set B that are in common between the two. So union is shown like this. I'm sorry. Union was all of it filled, intersection only the parts that overlap. It was sort of like when we were doing our graphing and we said this was the section where it went this way and then this way, but this is where they overlapped. That's intersection. And taking this a little further, suppose we had this, A intersection with B, but it would be an empty set. Well, then we'd have to redo our Venn diagram so it would look like this. There is no intersection. It's an empty set. All right, we're going to do some more on set operations and some basic primer on some of these things that you'll need for the next sections. One other term that I wanted to mention that I left out before was, again, there's no intersection between here set A and B, and we say that set A and B are disjointed. So that was one of the key terms that I left out. Wanted to be sure that's in. Now, as we look at a typical Venn diagram, there's our square, there's our set inside. The content of this whole rectangle is referred to as the universal set U. And anything inside it would be a subset of set U. U standing for universal. Now, it's not what is outside the box. It's everything inside the box. Now, notice that we have here set A, and then there's stuff outside the box, outside the circle, inside the box. What do we call the stuff outside the circle, inside the box? Well, we call that A complement. And it's written A with a little prime sign there. It's not the exponent 1, it's sort of like a slash. A complement. A complement. That's this portion outside. So if we were to sketch it, it would be this out here. The A would not be in that. So everything outside of A is A complement. Today we're having a guest lecturer who's going to help us out a little bit, Albert Navetta. Albert, all yours.
All right, so now we're doing example 4. We start with A union B. Remember, what looks like a big U is the union symbol, and we could replace that with the word or. So anything that is in either A or B, or we're taking all the elements of A and joining it with all the elements of B in this case. So all we have to do is look at A, 3, 6, and 9. 3 is also in B, but we're only going to list it once. And the order is not important, so we could, for now, just go 3, 6, 9, and then look over at B and list all the elements of B that haven't already been listed. So 3 we've already got, 4 we don't have, 5 we don't have, 6 we've already got, and we'll finish it off with the last element, which is 7. And that's it. That's our A union B. When we get into probability theory, it would be the same as saying the probability of A or B. Just a quick look into the future. Here we have the A intersect B, and we could say that that's the same as saying all the elements that are in both A and B. Remember, that symbol could be construed as the word and. So we'll just look at whatever's in A and B. So we'll just look at the elements one by one in A, and if they're also in B, then we'll go ahead and put it in the intersection. So 3 is in A and in B, so that goes in our intersection. 3. 6 is in A, and we also find it in B, so that goes in the intersection. 9 is in A, but it's not in B, so that's it. No other elements in B are found in A because there's only those 3 elements that we already looked at. So that's the intersection, that's all there is. Then we just do the same process for A intersects C. Remember, it's all the elements that are in both A and C. So we'll just do the same process. We'll start with A. 3 is in A, but we look over at C, it's not in C, so 3 doesn't go in. 6 is in A but not in C, and 9 is in A and not in C. So there are no elements that are in both A and C. So that's it. That is an empty set.
And the other symbol for that is the circle with the line through it. Yep.
We could also, some people used that in the past as a 0, but that's going to be now the empty set. And then we look here at B complement. That's just everything that's in the universal set, but not in B. So, all right, last we have the complement of B. The complement of B means everything that is in the universal set that is not in B. So what we'll do is we'll just look at the universal set and just go element by element. 1 is obviously in the universal set and not in B, so we'll list that. 2, we don't see it in B. 3 is in B, so we're not going to list that. Same with 4, 5, 6, and 7. All are in B. And then we go to 8 and 9. Those are not in B, so that's the complement, and that'll finish it off.
Okay, we thank Albert for his help on that last one. We're now continuing with example 5 on page 346. And this is very typical of how you will use set operations as you move forward. In example 5, they're talking about a marketing survey where they have 100 students and they're randomly chosen. And you might be involved in a survey every once in a while. For instance, do you own a TV? And of these 100 students, they answered yes. Now there was a second question. Do you own a car? And of these 100 students, 45 said yes. Then they asked the third question. Do you own a car and a TV? And 35 said yes. So we have data, and we want to analyze this data and present it, in a sense, as a set. So the Venn diagram that we spoke of earlier is useful here to analyze the data. And again, you'll be asked to do this on your practice and quiz me, so you want to be a little bit knowledgeable about it. So you have 75 for TVs, you have for the cars you have 45, and for both you have 35. So we know that there's going to be an intersection between our TVs and cars here, and how many will be in that intersection? And the answer is 35. So in our intersection, we put 35. But now, how many own TVs? Well, we said there were 75. So if we take the number 75, which was the total number, in fact, I can write that there. And the car was 45. So you get kind of an idea. But these are individuals that own both. So how many then just own a TV out of this 75? Well, in order to figure that out, and this is where the thinking about it comes in, if we have 35 of the 75 that are in this middle area, the intersection area, how many do we have over here? Just own a TV. So we subtract the 35 from the 75, and that now gives us a 40. And then we go to our cars. The 35 had a car and a TV, and we know that of the 45 then, how do we figure out just have a car and not a TV? Well, we subtract the 35 from the 45, and that gives us then a 10. So if you add these two numbers together, that gives you the 75. And if you add these two numbers together, that gives you the 45. So how many are in the TV set? 75. How many are in the car set? 45. But remember, there's an intersection between these two where there are 35 that have both. And that's how you would show it. And then the last thing, we want to find out what would be the complement of this union. That is, those that don't have a car and that don't have a TV. And you say, well, how do you figure that out? Well, you add up the individuals in this group, which is your 40, your 35, and your 10. Your 40, your 35, and the 10. So in this group that have either a car or TV, there are 85. But you asked in your universal group 100. So how many are the complement then of the union of this? That is, are not in that group. they don't have a TV or a car? And the answer is 15. You take your 85, how many more do you need to make the 100? And that gives you your 15. So this is basically the reason why we are looking at sets, where you're going to take information like this and be able to use it. Again, the key is put the ones here, and they're going to give you various challenging questions that you need to analyze in this way.